Well, hello. Today we're going to review a little bit on acids and bases to get ready for our test. So let me get right into this. We'll get started here. So one of the things I said you're going to need to be able to know are the names of common acids as well as common bases. Know both the formula, name, and a basic use for each of these. Let me just review these with you briefly. Hydrochloric acid is the acid that you would find in your stomach. It is also the acid used to clean off metal, any impurities on metal by dipping into it. That process of cleaning metal with hydrochloric acid is called pickling. The second acid I need you to know is sulfuric acid. It has the formula H2SO4. It is the number one selling chemical in the world. You would find it in car battery, that's battery acid. Phosphoric acid is H3PO4. It is a weak acid. It is used for food flavoring in beverages. Oftentimes we like things that are sour, so a little bit of phosphoric acid helps enhance the flavor. Nitric acid, HNO3, is a strong acid. It is the one that if you got on your hands would stain your fingers yellow. It is also used in the manufacture of fertilizers and explosives, such as ammonium nitrate. Acetic acid has the formula CH3COOH, is a weak acid. You would most commonly encounter acetic acid in your kitchen. It would be called vinegar, and it's a 3 to 5% solution of acetic acid dissolved in water. The last acid we haven't mentioned for a long time is hydrofluoric acid. Hydrofluoric acid is a weak acid but extremely dangerous. It is used to etch glass. If you get it on your skin, it will absorb into your skin and then start to dissolve your bones, which you can obviously see that would be a very, very bad thing to have happen. It must be stored in plastic. It cannot be stored in glass or will eat through the glass container. So even though it's a weak acid, that doesn't mean that it's a safe acid to use. In terms of bases, I've listed three here that I'd like you to know on the bottom of the page. Sodium hydroxide, which is also called lye. It's what we use to make our soap. Calcium hydroxide. This would be a main ingredient in concrete. It makes concrete from the calcium oxide after it slakes in the water. It would also be an impurity that you're going to get in water that's going to spot and leave spots all over your glass in your bathroom shower. Ammonium hydroxide is also just called ammonia dissolved in water, is our last example of a base. One thing I would like you to recognize is all bases, or at least these that I'm showing you, have a hydroxide and OH in them, and that's what makes them a base. We had talked about who developed the pH scale. It was Soren Sorensen. That's a little bit different than the pH meter. The pH meter was invented by Arnold Beckman. He was a graduate of University High School here in Bloomington, Illinois. The pH scale measures the hydrogen ion concentration in a solution. If you have the proton concentration equal to the hydroxide concentration, you would be neutral at pH 7. If the hydrogen ion concentration is greater than the hydroxide ion concentration, you would be in the acid range, or it'd be considered acidic with a pH less than 7. If the hydroxide concentration is greater than the proton concentration, it's alkaline, or another term for that is it's basic. So bases have a pH greater than 7, acids less than 7. Please remember, if something has a pH of 7, it doesn't necessarily mean it's safe to drink. You can have a poison, add acid or base to it to neutralize the pH, but it still contains poison. So the term here for bases are alkalinity, and for acids, acidity. I mentioned Arnold Beckman invented the pH meter. That's probably only important if you're in my class and you want to get that multiple choice question right about either who invented the pH scale or who invented the pH meter. We have here an example of a formation of, here's an acid dissolving in water, and then it forms a hydronium ion. So we start with a proton, we put it in water, and we form a hydronium ion. We're going to treat a proton and hydronium as equivalent species because protons don't really exist in chemistry outside of water. We went through some equations, and I'll just review with you the main equations. pH is opposite log of H plus. POH is opposite log of OH. Then we have pH plus POH is 14. And then finally, we have the Kw value for water is equal to H plus times OH minus, where Kw is 1 times 10 to the negative 14. All right, we then spent some time discussing the difference between concentrated versus dilute. And the way we use this concentration is units such as molarity or molality or normality. So let's just review these briefly. So molarity is capital uppercase M, is moles of solute over liters of solution. And that's typically what we use in a high school chemistry class or any laboratory to be measuring concentrations. In a more industrial setting, you might use a term such as molality. Now, molality is a lowercase m, is moles of solute divided by kilograms of solvent. And we discussed if you're making very large batches of medicine or something on an industrial scale, instead of weighing out 60,000 liters of some solution, you're going to simply mass out that many kilograms by having your entire mixing vessel on top of a balance, some kind of scale. Normality is not one that I'm going to cover in this class. If you were in my class, you heard me use this term. Let me just describe what normality is, and we'll leave it at that. If we take sulfuric acid, which is a diprotic acid, it's a strong acid. It will generally dissociate and produce 2 protons and a sulfate ion. If you start with 3 molar sulfuric acid, you will generate the equivalent of 6 molar sulfuric acid. The proper term for that would be normality, but I was trying not to confuse you, so I just always held my fingers up and said 6 molar. And so I'll continue to do that as long as we understand that it donates 2 protons, and effectively it's as though it's a 6 molar solution. Hopefully that makes sense to you. Now that's a little bit different than strong and weak. Strong has to do with a complete dissociation of the molecule where 100% of the acid ions are produced. A weak acid, on the other hand, is a reversible reaction, in which case you get, maybe 20% or less dissociation. I have here a monoprotic. It can donate 1 proton and an anion. And here's a representative of a diprotic, such as, sulfuric acid is strong, but if we had a weak diprotic, it would donate 2 protons and an anion. So if this were like 2 molar, this would be the equivalent of 4 molar if it's strong, but because it's not strong, we have to use the Ka calculation. So Ka is the acid dissociation constant for a weak acid. It's always equal to the concentration of product divided by reactant. Using the equation above, if I wanted to write an equilibrium expression for that, Ka would be equal to the concentrations of the product, H plus times A minus, divided by the reactant, H2A. Because there's a coefficient 2 in front of the hydrogen ion concentration, whatever the proton concentration is in the Ka expression must be squared to take that into consideration. So that's important to recognize. This squared comes from that 2. In terms of acid dissociation constants, I told you that if you have a very large number, that's a strong acid. So phosphoric acid has a relatively large Ka of 0.8, whereas hydrofluoric acid, a weaker acid, is 0.0021. Acetic acid, if you're remembering, was 1.8 times 10 to the negative 5th, or 0.000018. So acetic acid is a much weaker acid than hydrofluoric or phosphoric. Let's look at and remind ourselves of properties of acids and bases. Acids have a sour taste and will turn litmus red, blue to red, acid. Bases, on the other hand, have a bitter taste and will turn red litmus blue. The definition of an acid from Arrhenius is a proton is the only ion produced in water, according to Arrhenius. For a base, the definition of a base, Arrhenius says, produces hydroxide as the only ion in water. The Bronsted-Lowry definition of an acid is a little bit broader. It's anything that donates a proton, and the base is anything that accepts a proton. So here the big difference is Arrhenius said an acid was a proton donor, a base was a hydroxide donor. But now the base for Bronsted-Lowry doesn't have to have a hydroxide as long as it gets rid of or accepts a proton. Anytime you take an acid and a base, it will undergo what's called a neutralization reaction, in which salt and water are the two products. So let's pretend we need to make the salt calcium sulfate in the lab. So I know that the sulfate, calcium sulfate, is my product, and I know water is one of the other products. So what acid base would I need to make this work? Well, the acid is always going to be H with something else, such as SO4. So I would suggest we put sulfuric acid in here. That'll donate protons, leaving the sulfate behind. The base has to have a hydroxide with calcium, so let's go ahead and put calcium hydroxide there. What will happen is the calcium and hydrogen will switch places. We will indeed produce calcium sulfate, and our byproduct will be water if we take the time to work that one out. Most of the time, chemists just buy the salts they need, although with enough acid-base combinations, you can make any that you want. In terms of indicators, there's a few that we use in the lab. We use phenolphthalein with our strong base, sodium hydroxide, titrating the weak acid, acetic acid. And it was colorless when it was in the acid. And as soon as we added enough base to reach the endpoint, it turned that pink color. So phenolphthalein is the indicator of choice for a weak acid, strong base. When you were using a strong acid and a strong base, we use very dilute hydrochloric acid and very dilute sodium hydroxide. The bromethymol blue would be the indicator you want to use. It will reach an endpoint around 7, so it'll change yellow to blue. And a few of you were good enough with the burettes where you were able to get your solution to stop at green. Nicely done. Universal indicator would not be used in a burette because it tends to change the colors of the rainbow, and it's hard to know when you've reached what's called the end point. It's not as dynamic of a range as red cabbage, but it doesn't have an odor. It will generally range from about pH 4 to pH 12, which for most lab situations in a high school lab is just fine. Finally, we have litmus paper and pH paper. Now, based on these, I guess we could also add a pH meter. The pH meter would be the most precise method, then the pH paper, and then the litmus paper would be the least precise. Bromethymol blue and phenolphthalein reach an endpoint, wouldn't be very good at doing anything other than that. Buffers, we talked about that buffers, by definition, are salts of weak acids and weak bases, and they help to maintain a pH. If you remember from Halloween, we poured different cups full of liquids, and they changed the different colors of the rainbow. And what we had done is we had left buffers in the bottoms of the cup with universal indicator, and it changed colors based on the buffer. Some things that might have buffers in it, you remember, aspirin, the actual name of aspirin is acetylsalicylic acid. That's a weak acid, and if you take too much acid, it can cause an upset stomach. So a chemical company, Bayer, decided to make buffered aspirin, and they call that buffered aspirin bufferin. And basically, it allows you to have the acid in it but it won't. It's sort of like putting guardrails on a road. It won't let you go over the edge one way or the other. So the buffer maintains the pH. We had discussed Le Chatelier's principle with relationship to equilibrium reactions. Remember, Le Chatelier's principle states if a system is disturbed or stressed, it will respond in a way to relieve the stress. I gave you a couple examples of this, acidosis and alkalosis. These were conditions of the blood, in which case your blood pH would go below 7.2, that was called acidosis, or above 7.4, alkalosis. The ion in your body that acts as a buffer to maintain your blood pH is called the bicarbonate ion. A source of the bicarbonate ion would be the bread that we eat. We use the example of glasses, transition glasses, that when you go outside darken. Again, go back and review that as how that applied to Le Chatelier's principle. And finally, we had discussed the thickness of eggshells. When chickens pant, they have less CO2 in their bloodstream and will produce much thinner eggshells. So the solution for the eggs were to give the chickens carbonated water to raise the level of carbon dioxide in their body so they could add more carbon dioxide with the calcium oxide to make thicker eggshells. We looked at acid-base concentrations. Remember that if you have an acidic solution, you have a higher quantity of hydronium ion in solution than hydroxide. On this graph, this has a concentration of 1 times 10 to the negative 7th, negative 8th, 9th, 10th, 11th. So this would have a pH of around 11. And excuse me, I misread that completely. Here's 10 to the negative 1st, 10 to the negative 2nd. How about 10 to the negative 3rd? The middle one, the hydrogen ion concentration, is 10 to the negative 7th, pH is 7. And the last one here is 10 to the negative 11th. If I go down, go across, that's the hydrogen ion concentration. We talked briefly about things that are amphoteric, that is, can act as an acid or a base. So let me just remind you a little bit. Here's ammonia, NH3. Here's the structure, NH3, with a lone pair of electrons. Now, what can happen is one of these hydrogens on the bottom can just leave. As this one leaves, it loses a proton. It leaves behind its electron. So there's an extra negative charge. And this is called the amine group, NH2, 1-. So ammonia can produce or give up a proton, and it acts as an acid. Likewise, because ammonia has this lone pair of electrons, it can, in solution, accept a proton that's in solution. It makes a coordinate covalent bond, that is one atom. The nitrogen provides both electrons, and because the hydrogen brought on its positive charge, this entire molecule gets a 1+ charge. So in this case, ammonia was acting as a base as it accepted a proton to form the ammonium ion. Now, perhaps you've heard of these different things, like if you've heard of amino acids, these are the things you had to match up, the CG, UC, and so on in biology. If you looked at the structure of amino acids, they all have an amine group, and they all have a carboxylic acid. A carboxylic acid has a C double bond O, OH on it. That's what makes something a carboxylic acid. Okay, I think that will basically cover what you need to know for tomorrow. I don't think we need to go through anything else, so hence we will stop talking for today. Let me kind of close off here and say good luck with your studies. Send me an email if you have any questions. Take care and good luck. Bye-bye.